Well, here we are, the first truly new lesson of the course, introducing the idea of a limit. That's what this next unit is called, limits. You've, in a sense, you've been kind of introduced to this informally in pre-calculus 12 when dealing with rational functions and these points of discontinuity and this idea of having these infinitely small gaps. That's it. What you see here is a graph of f of x, which is x squared minus 1 over x plus 1. And that's what you see is this graph. However, it simplifies down to a linear function, but it still has this restriction where x cannot equal negative 1. Just by looking at the actual expression here, I can just see immediately. If x is negative 1, I'm dividing by 0, which means I know x, when x is negative 1, I have a break in my graph. Yet, if you factor it and simplify it, it simplifies down to a linear function. Hence, it looks like a line. And so I say, oh, that's not a highlighter. It says, notice the discontinuity at negative 1 comma negative 2. Okay, notice that discontinuity. Even though f of x is undefined when x equals negative 1, so that means only at negative 1 is this function undefined, but we can get infinitely close to negative 1 and the function is still defined. And as we get infinitely close to negative 1, the function gets infinitely close to negative 2. And again, that's what these little arrows are showing us. Even though when x is negative 1, this function has this point of discontinuity right there, as we approach from the left or from the right, as we get infinitely close, the y value, the output, gets closer and closer to negative 2, infinitely close to negative 2. And so even though the function is not defined there, we can get infinitely close to that point. And so it's like the function behaves in a sense that when x is negative 1, it doesn't equal negative 2, but it gets infinitely close to negative 2. And that idea is what is being described right here with this notation in green. The way we read this is we say the limit of f of x as x approaches negative 1 is negative 2. So this is not the same as saying f at negative 1 equals negative 2. This is saying as we get infinitely close, it equals negative 2 from both sides. All right, but that's it. That's probably new. So most of what this first lesson is trying to get a sense and a feeling for how to read the notation and really what this means. So what I have now is a different function, g of x. All right, and I'll just kind of label this here. And I want to evaluate all these limits. That's it. A lot of these limits, notice these limits here have either negative signs or plus signs in superscript, which means it looks like an exponent. So these represent what we call one-sided limits, which is the exact same idea, but we're focusing on just as we approach from one particular side. And if we see a negative sign, that means we're approaching from the left. If we see a plus sign, that means we're approaching from the right. And so let me just kind of look at these. For example, if I look at the first limit here, when x approaches 1 from the left, that means, if I look at my graph, here's where x equals 1. I'm paying attention to as I approach from the left, as I get infinitely close to 1. Well, as I get infinitely close to 1 from the left, the output gets infinitely close to 2. And so even though I never reach that point, I get infinitely close to it. And so if I was to ask you what is g at 1, I would say it's undefined. This function is literally not defined. When x is 1, there's nothing there. But I'm not asking what's g at 1. I'm asking what's the limit as we approach 1 from the left. And for that, we say this equals 2. Well, this next limit is that little plus sign there means the exact same idea, but we're approaching from the right. So I want to imagine looking at this curve and getting infinitely close from the right towards that point. So what's the limit? What's my output getting infinitely close to? Well, again, it's 2. So in this case, regardless of the fact if I'm approaching from the left or the right, I get the same value. And anytime we have the same limit when we approach from the left or the right, then that means if we just say, what's the limit as we approach 1? Notice there's no plus or minus here. That means we call this a two-sided limit. And that's what we saw kind of just above. In this case, if we have the same value from the left or the right, then it's just that value right there, 2. So in this case, the limit as we approach 1 from the left, the limit as we approach 1 from the right, and the limit as we approach 1 are all the same thing. And so before I look at another example, these are called one-sided limits. This is called the two-sided limit. And what if the left and right sides aren't the same? Like when we approach 3 from the left or from the right. So now let's pay attention to this point here. right? When x is 3, I have this break in my graph. All right, so first, let's approach 3 from the left. That means from here. As I approach from the left, I get infinitely close to this point here. I never reach it, but I get infinitely close, and that point there has an output of 2. This equals 2. Okay, let's approach from the right. I get infinitely close to this point here. It is defined, but that doesn't matter though, because once I actually get to that point, that is actually at 3. And again, if you look at this limit, I'm approaching 3 from the right. I'm approaching it, but I'm never actually reaching it. And again, I appreciate if that's kind of a weird abstract idea, but so it doesn't matter if that's a filled in point or not. As I approach 3 from the right, my output is getting infinitely close to 1.56. In this case, notice these are not the same. And so anytime you have limits approaching from the left and the right that are not the same, then if we just ask for the limit as we approach 3, then we say it does not exist. I'll make my writing a little bit neater there. And so if a limit does not exist, that means we don't get the same value when we approach from the left and the right. If we do get the same value, the limit exists. In the previous case up here, it equaled 2. So lots of new things here. The focus of a lot of what I'm looking at in this lesson, again, is getting a sense for what these things mean. And so right now, though, we've introduced the key ideas. What a limit is, it means you're getting infinitely close to a value, and a left and a right side limit, which means we're just coming from one particular side. All right, the best thing we can do, though, is just look at some other examples. So what I have here is a pretty weird graph of f of x. Okay, a lot of stuff going on. I will say there is a vertical asymptote at -4, so I'm going to draw this vertical asymptote here. Now you may be kind of thrown off by the fact that I drew an asymptote that a point goes through. But functions can go through an asymptote. All this asymptote means is at some point, this function gets infinitely close to it forever. And that's what's happening down here, right? But, you know, in this particular function, yeah, it still goes through the asymptote later on. But again, all an asymptote really means is at some point on that asymptote, the function gets infinitely close to it forever. And that's exactly what we're seeing here as we go down. As well, I like to show that this function goes forever to the left, but has an endpoint right here. So the function stops right there. And endpoints are a little bit special, which I'll talk about in a bit. That's it. I got a whole bunch of limits here, which is great to kind of be able to look at a whole bunch of possibilities. So first, I want to ask, what's the limit as we approach -4 from the left? That's what this means. As we approach -4 from the left. So the asymptote's at -4. As we approach from the left, we're going this way, down forever. And so in this case, we never reach a number, but we are going down forever. And the closer we get to -4 from the left, the more and more down we go. And so we say, in this case, the limit equals -infinity. Now again, infinity is not a number. It always looks kind of weird when we say something equals infinity, but this is essentially just notation or convention, and this just tells us that what we see, that this goes infinitely down forever. But again, please don't think infinity is a number. What if we approach 4 from the right? Sorry, -4 from the right. So we approach -4 from the right. We're looking at this point right here, and we get infinitely close to 3. So notice my limit from the left and the right do not agree, are not the same. So right away I know if I just ask what's the limit as we approach -4, then I know this does not exist. And quite often we just write dne. And what if I just ask what is f at -4? This is just function notation. This has nothing to do with limits. But it's good to review. F at -4 means literally what is the output when x is -4? Well, when x is -4, we look at this point right there, and it's a nice clear point, and so this equals 3. All right, so similar examples. Let's look at, and to be honest, what I would recommend for the rest of these is just to pause the video and try all of these. You'll probably make a few mistakes. Maybe you'll make a bunch of mistakes, but either way, that's way better than just watching me do every one. But I do recommend you pause it at this point and just try some of these on your own. That's it. I'm hoping you paused. So next I'm focusing on 0, from the left, from the right, from both sides, and just f at 0. And I can do these in any order, really. But I'll do them in order from left to right. So as I approach 0 from the left, let's look at, as I approach from the left, well, as I approach from the left, this graph gets kind of crazy. And what's actually happening here is this little section right here is oscillating up and down faster and faster and faster. And so what's happening right here, it's actually just literally oscillating faster and faster forever the closer you get to 0. And that's why it looks like this solid chunk of green. It's not actually solid at all. It's a wave that the period just keeps getting compressed infinitely so the closer you get to 0. And even though I did make this in Desmos, I don't have it handy on me right now. If I were to zoom in on this, you would see that no matter how much I zoomed in, this area here just keeps oscillating faster and faster. The period keeps getting compressed forever. And there's no limit to how much I can zoom in, so there's no limit to how much this can get compressed. So that's why it looks kind of weird. What is the limit then as we approach 0 from the left? Well, I can't say, because it keeps oscillating forever. And so the limit as we approach 0 from the left, we say does not exist. What about when we approach 0 from the right? Well, that's a bit simpler. As we approach from the right, we're looking right there. And as we approach from the right, it gets infinitely close to 5. Again, it never actually reaches 5 if we think about a limit, because we're not actually ever getting to 0 with the limit. We're getting infinitely close. And so we say this equals 5 means we're getting infinitely close to 5. That's it. What's the limit as we approach 0? Again, the left and right side limits do not agree, so automatically this does not exist. And what is f at 0? This is the only time we actually look at 0, and when x is actually equal to 0, again, that same point, I guess I shouldn't have erased it, right there. So that is clearly defined to equal 5 when x is 0. All right, let's approach 3 from the left, right, and so on. So we approach 3 from the left. So I'm looking right here. The limit as we approach from the left equals -4. I'm getting infinitely close to -4. What about when we approach from the right? So we approach from the right. I'm looking right here, getting infinitely close to 5. So right away, I don't even need to look at my graph again. I know the limit as we approach 3 is just going to be does not exist. And what is f at 3? Well, now I'll look at my graph. When x is 3, which is right here, both of these are open points, which means my function is not defined when x is 3. And so that's I literally say this is undefined. A little bit of terminology here. Generally, with a limit, we shouldn't say a limit is undefined. We say either a limit exists or does not exist. A function, we say it's either defined or not defined. If it's defined, then we get a number. If it's undefined, it's undefined. We say undefined. So try to keep the phrase does not exist to limits and undefined to the value of the function. It's easy to mix them up. It's not a big deal, but we might as well try to get used to that. Lastly, 6. As we approach 6 from the left. Now 6 is an endpoint. So like I said, there is something special about endpoints. That's it. As we approach from the left, that doesn't really matter if it's an endpoint or not. I can see I'm getting infinitely close to 4. Sorry, -4. As we approach from the right, well, there's nothing there. My graph, there's nothing there. It's an endpoint. So the limit does not exist, so we approach from the right. So you may be tempted to say that the limit, therefore, as x approaches 6 does not exist. But because 6 is an endpoint, so I'll say x equals 6 is the endpoint of f of x. So because of that, when we're dealing with an endpoint that's on the right, for example, like we see here, then we ignore this part right here because there's not even a function there. And this is just for endpoints. And so in this case, the limit as x approaches 6, we say does equal -4. And again, it seems like, well, I did kind of contradict what I said earlier about if the two one-sided limits don't agree, then this will not exist. The only exception to that is when dealing with endpoints, the actual end of the graph. Not just a break in the graph, the actual endpoint. And a lot of functions don't have endpoints. In fact, most functions you've dealt with over the years don't have endpoints. They have a domain of all real numbers, and they go forever to the left and the right. So don't assume all functions have endpoints. That's it. F at 6. Again, look at my graph. The output when x is 6 is, again, -4. And so all of this sort of stuff here, with a bit of practice, gets quite doable. But you need a bit of practice. There's a lot of little details to be clear about, including stuff like the endpoints here. But now I want to start talking about what if you don't have a graph? Well, one option is to make an educated guess using substitution. And that's what I want to look at here. Eventually, we want to look at ways of making not just educated guesses and without substitution. But right now, I want to focus on just the idea of making an educated guess using what we call substitution, which, like it says, is we're going to use a calculator to make an educated assumption and then use that to make us an educated guess. Eventually, we'll come up with better ways. So what's the limit as a approaches 0 of this? Okay, I don't know. I don't have a graph. And not only that, if I just look at this function, 1 plus a to the power 4 take away 1 over a, it's too complex to kind of be able to visualize immediately. So how can I answer this? Well, this idea of using substitution is to pick a number that's really close to 0 but not actually 0. And again, you can actually pick 0 if you want, but notice if I pick 0 if I pick 0, I can see right away my denominator is going to be 0, and there's no point me even trying to calculate anything. Once your denominator is 0, it's undefined. So, but the idea is we're not actually reaching 0, we're getting infinitely close to 0. And so, I don't know, let's pick negative 0.01. So I'll say let a, I should say, equal negative 0.01. Right, I think that's pretty close to 0. Now, there is no number actually closest. Why not put 0.001 or 0.0001? The idea is just pick a number close and see if we can, again, make a guess, an educated guess. So when I let a equal negative 0.01, this expression becomes 1 plus negative 0.01, all to the power 4 take away 1 over negative 0.01. Now we go to my calculator. And I go to a calculator and I evaluate this, and I get about 3.94. Okay, that's it. This limit is a two-sided limit. It says as a approaches 0, not from as a approaches 0 from the left or the right. So I also need to pick a number that's close to 0 but more than it. So how about positive 0.01? Same thing. So I get 1 plus. And again, go to my calculator. And for this, I get approximately 4.06. So here's where I make my educated guess now. As I approach from the left, it's a little bit less than 4. As I approach from the right, it's a little bit more than 4. So my educated guess now is to assume that this equals 4. Exactly. Now that's it. Do I know that for sure? No. Do I feel pretty good about it? I feel pretty good. If I want to feel better, right now I could just pick numbers even closer. I could substitute a with negative 0.000001 and positive 0.0001. Just realize there's no limit to how close you can get. And I will say, if you do that, you keep getting numbers closer and closer to 4. And the more you do that, the more confident you can feel. But right now I'm just looking for an educated guess. And eventually we'll come up with something better than that. There we go. Equals 4. Okay? And it does actually, but again, I got a sense. This doesn't actually prove anything, but it gives me an idea. And again, it's an important idea to start with. We don't want to forget what a limit is. We're getting infinitely close from the left and the right. So let's look at this one here. As b approaches 9, okay, of this expression here. Again, I can't tell what this looks like right away, but I can pick a number really close to 9. And so for this, I'll say let b equal, I'll start with 8.99. And so this expression becomes 9 minus 8.99. All right, type that into a calculator, and I get about 5.99. Okay, and it's really close to 6. So I already have a pretty good sense. This probably equals 6, but let me pick that was from the left. Let me pick a number a little bit more. So 9.01. And notice if you actually replace b with 9, which is not a bad idea, but you'll immediately notice you're dividing by 0, so it doesn't do us any good. And so I have 9 minus. Type that into your calculator, and I get just a little bit more than 6. So I feel pretty good then that this limit is probably 6. And so last one, and again, I would encourage you to try this on your own. Pick two numbers, one a little bit less than 2, one a little bit more than 2. So I'm hoping you kind of try this. I'm going to pick, for 1.99. If you do that, you get about negative 0.2512. It's pretty close to negative a quarter. Let's see if I put a number a little bit more than 2. And I get a number a little bit, just a little bit off from negative a quarter again. So both these are very, very close to negative 0.25. Both these are very close to negative 1/4. So my educated guess, and again, we can't lose sight of the fact that I'm really just making an educated guess for all of these, so it should be negative 1/4. But I feel pretty good about these. Now, pretty soon, especially by the time I assess you, we'll have better strategies than this. But it is a good place to start, and it really just reinforces one of the key aspects of limits is that we're not approaching, in this case, we're not actually ever equaling to, we're getting infinitely close, and gives you a little sense of what these are at. All right. The last thing I want to do is look at two limits that are quite important, especially the first one. And so, especially this limit on the left, the limit as x approaches 0 of sine x over x is a limit that will keep coming up throughout this course. And once we see what it is, we want to memorize it. That said, right now I'd say use substitution. And so again, I highly recommend you do this on your own first. Pick a number a little less than 0, a little more than 0, and it should become quite clear, I hope. That said, pause the video. I'm going to assume you have. And so at this point, if you pick, I don't know, negative 0.001 and positive 0.001, you both get numbers really, really close to 1. And so you can make an educated guess, which is correct, that the limit as x approaches 0 of sine x over x equals 1. And this is an extremely important limit, and we want to memorize this. All right, another limit that's pretty important but not as important is this other one here. Again, I'm assuming you've already tried this. Pick a number a little less than 0, a little more than 0, and you should find this gets really close to 0. Both these will come up again in later lessons involving trigonometry, but right now, that first one, try to make a point of just memorizing the limit of sine x over x as x approaches 0 is 1. Even though, notice again, if you literally just replace x with 0, you get the sine of 0 divided by 0. The sine of 0 is 0 divided by 0, and this is undefined, right? And that's kind of something we see all the time when dealing with limits. If you just literally substitute the value in, you can't do much because you're dividing by 0. I don't really care what the numerator is, you're dividing by 0. And yet, when we put numbers really, really, really close to 0, in this case, we get really close to 1. All right? So that's it for this first introductory lesson on limits. I think it's a good place to stop.